Now, I would like to request our honorable program chair to please give a brief intro for today's speaker, Dr. Petia. Sir, it is over. Ma'am,
Okay.
I'm very sorry for this delay. Please don't mind. I'm very sorry.
So Professor Radeva, sorry for the delay. So being the program chair, I just introduced Professor Radeva. Professor Radeva is a full professor at the University of Barcelona and PI of Consolidated Research Group, Computer Vision and Machine Learning at the University of Barcelona. And he is a senior researcher center. She was PI and UB of 4 European and 3 international, more than 20 national projects to applying computer vision and machine learning for real problems like food intake monitoring. Professor Radeva is a Reafet Open Vice Chair since 2015 on an international mentor in the Wildcards EIT program since 2017. She is an associate editor of the Pattern Recognition Journal, an international journal of visual communication and image representation. Professor Radeva has been awarded IAPR Fellow since 2015, ICRA Academic assigned to the 30 best scientists in Catalonia for her scientific merits since 2014, received several international awards and prizes for the best technological transfer of UV. She supervised 18 PhD students and published more than 100 SCI journal publications, 250 international chapters and proceedings. Our Google Scholar Index, H index is 44 with more than 7,600 citations. So I request Professor Radeva for his talk on food image analysis by deep learning. I welcome Professor Radeva. Thank you.
Thank you very much. Good afternoon. Do you hear me well?
Yes.
Yes, ma'am. Clear.
So thank you very much for inviting me. It's a pleasure to be able to talk to you, to explain our research, our project in food image analysis by deep learning. This is a project that is developed in a collaboration with my PhD students, Eduardo Aguilar, Marc Bolaños, Ballav, and Ropario. So today I want to go briefly, because we will not have so much time to go into details, but try to explain why we work on food image analysis and food recognition. Because God you hear me well?
Ma'am, just wait. Professor Paul, Samarjit Paul, please mute yourself. Professor Paul, you are having the control. Please mute all the participants, excluding Petia ma'am. Okay, ma'am, you can continue now.
So if we look, for example, in Instagram, we can find 180 million of images and documents that were hashed by the hashtag food. And there are 90 messages and images that are uploaded every minute. And if we think about who is data about food, you can see that 45% of the people take pictures of their food, and 55% of them posted in the social network. So today we have big amount of data, big amount of images on internet, and that's why we can work on them and get a nice profit. But why is the food recognition a challenge? Because if you have a look in this food recognition in a problem, so well, let's see, for example, in these images, you can see that there is a big variance. So if I ask, for example, what is this? Maybe some of us will say this is a carpaccio. Maybe some of us would say that this is tomato. Or if, what is this? Also, maybe some of us will say this is a steak, but maybe some of us will say that this is a duck. And what is this? Maybe it is spaghetti, or maybe this is fideuà, or what is this? Maybe this is chocolate cake, but also it could be many other things. So that's why we speak that in food we have very big intra-class variability. Within the same class we have a lot of differences, but we also have very big inter-class similarity. That is, two different classes can look very, very similar. So that's why it is this problem of interclass similarity and interclass variability is making the problem, its precision going down. So how do we approach this problem? Now we see how we approach it. When we have a picture of food, in this picture we can make several questions like what is the cuisine, what is the category of the dish, what are the ingredients, and what is the dish. So all these problems are different classification problems. So that's why we are speaking about the different tasks or different classifications. And instead of having different models to answer to the different questions, what we can do is we can have one and the same model, and that is addressing all different tasks. And this is called multitask learning. And multitask learning has been shown that it is much more efficient and accurate because we have one model that share information so that one task can help to the other, and in this case help in the different difficult cases. And also it is less computationally expensive because instead of training four models, we train only one model. And also this do the well-known deep learning property that is knowledge transfer or transfer learning, because it is sharing information, and in this case it is generalizing better the model in order to address the different tasks. So in deep learning, usually what we do is we do fine tuning. We train our network on ImageNet, for example, and then we get this network as initialization. Then we change the last layer to apply, for example, for the food, and then fine tune to our new problem. But in the multitask problems, what we have is different tasks. So it means that at the end, we don't have to have only one layer, but we should have several layers. So in our multitask learning problem, what we can do is to construct a neural network so that it should have some shared layers in order to share information between different tasks. But at the end, we should have different layers that are specialized to the different tasks. And in this way, we will have a multitask learning model. And here, different questions appear. How to construct the right architecture? Does it depend on the final task? Should it have a completely shared representation between tasks, or only a few layers that are shared between the different tasks? Or should we have a combination of shared and task-specific representation? And is there a principled way of answering these questions? So all these are open questions, and there is no answer of this. But there is one more question. How to construct the loss function? That is, we have one model, and this model, when we train on this problem, so the way to train a neural network is by minimizing its loss function. But in our case, we don't have one classification. We have four classification problems. So we will have four errors, four kinds of error for the cuisine, for the category, for the ingredients, for the dish. So we will have four loss functions. So in order to determine the loss function, the whole model, we can make it a function of the loss functions of the different submodels or the different tasks. And then we need to combine this, and in order to combine, we can put some weights. So how to determine these weights? Are they uniformly weighted? Are they manually tuned? We can do both of them, but what about to try to determine this weight in a more intelligent way? For example, I have different tasks, and some of the tasks will be easier. So if some of the tasks are easier, I want that they help to the other task more. So I want that the priority or the weight of this task should be higher. And at the same time, if I have some of the tasks like ingredients recognition that has a lot of error, a lot of noise and uncertainty, so I don't want that this task is influencing because it will propagate the error to the other task. So in this case, I want that this weight is is lower. So what about to do this weight, to determine this weight as a function of the error or as the function of the uncertainty? So this is what we try to do. But now we should speak about the uncertainty. So why do we need uncertainty? So because we are doing machine learning, in particular deep learning. So usually in the machine learning problems, always the question is why my model is not working. But in deep learning, we are getting so well performing models. So now sometimes the problem is why does my model work? And we don't understand completely many of the tools that we are using. For example, shall we use stochastic gradient descent? Shall we use dropout? Shall we use regularization? How to avoid over a lot of questions and tools and tricks, and it's not always very clear what we are doing and why should it be working. So this is known as the problem of the black box of the deep learning. So many times still a lot of people we are using as deep learning models as black boxes. We put input, we train, and we come up with some model, and then we have this output. But how the decision is taken, we don't know. And that's why today the explainability problem is really a hot topic. But we are not only and one we don't only want to understand why the decision is taken, but we also want to know what is the uncertainty, because we can think many situations the for the decision should be really reported to the final user with the uncertainty of having it. For example, let us imagine that we go to a physician and physician consider a radiography, and then for algorithm of deep learning is saying, okay, this person has cancer. And then the physician, without understanding why the algorithm say there is a cancer and what is the certainty to say cancer, the physician consider that it is necessary to go for operation. So we cannot believe to the algorithms if we don't have their uncertainty with which they give us their solutions. So let's think about how to determine the uncertainty and where does it come from. For computer science, as most of us, we used to work with algorithms, and algorithms are full function and they are deterministic. So we put the input, we get the data, we get the answer, we get the output. So this means that for this kind of input, we have only one solution. That's why it is a deterministic procedure. But in machine learning, it is not the same. That is, in machine learning, sometimes we can have not necessarily clean and certain answer. And it can be surprising that machine learning might have used a probability theory in order to relate the answer with the uncertainty. But that's why the reason that the answers aren't known is because of the uncertainty. And that's why many times we need to do cross validation, tenfold cross validation, or five-fold cross validation in order to systematically evaluate different solutions until we get a good enough set of features and algorithms for a specific prediction problem. So that's why there is always noise in our data. And this noise refers to the variability or randomness in the observation. And the real world in turn is messy or imperfect, as we know. So we should be skeptical when we consider our data and develop our systems in order to harness the uncertainty of the answer. And one of the serious reason for this is because the coverage of the domain is always incomplete. There is always bias when we get the data. We never will have all the data necessary or sufficient in order to train our models. And there is a big variance in bias in the sample required. So maybe we are training our deep learning algorithm to detect cancer in mammography, but maybe we are using only Spanish population. So there is always bias. And often we have a little control over the sampling process. We don't know how to avoid the bias in choosing our data. And also, in all cases, we will never have all the observation. And that's why our data will be imperfect. And that's why we split many times data set into train and test and use resampling methods like K-fold cross validation. In order to do this, we do this to handle the uncertainty in the representativeness of our data and estimate the performance of a modeling procedure, not bad procedures. So this is often summarized as all models are wrong. That is, that we are quite aware. But also it is true that, as somebody said, like George Box, that all models are wrong, but some are useful. So that doesn't mean that we should think only about the wrongness of the model, but we should consider that there is uncertainty in the whole process, in data, in model, in artifacts, and in the final training solution. So another type of error is an error of omission. In many cases, it is more practical to use a simple but uncertain rule rather than a complex but certain one. That is, this is many times in machine learning, we recommend to use the Occam razor. So try to work with more simple as possible model to solve the problems. And that's why, for example, some years ago, multiple classifiers were very, very useful. So given we know that the models will make errors, we handle this uncertainty by seeking a model that is good enough. And the uncertainty, in fact, was one of the main reasons of the fatal accident of Tesla, when the algorithm of Tesla car was not able to distinguish this shine effect, and it just considered that the road is empty. So the car proceeded. So let's try to specify a little bit the uncertainty. So for example, let us think about this simple example. If we have trained our model only on fruits classes, and then our model is looking on a picture of chocolate cake, what do you think our model will say? Probably it will say one of the fruits, because it never knows that there is another class called chocolate cake. And for the reason for this is the responsible for this is the softmax that is pushing, that is imposing us always to give an answer. Or another example, when we have different classes, and maybe some of the classes can come with much more error than other classes. So do we think that our models are able to distinguish the noise or the uncertainty of the different classes? So this is also not true. Or our model can have different also error, can introduce error. For example, if we consider here a regression problem that is trying to interpolate this data, so if our model is too simple, it will always have some error. If we use higher order model, it will fit much better. But even if we have a much higher order, it will get even less error, but maybe it will overfit. So if I have here a new data in the middle between this, it will get a lot of error. So this is the phenomenon known as overfitting of the models. So that's why we speak about aleatoric uncertainty that is coming from the data, where the noise is coming from the data, and epistemic uncertainty when the noise is coming from the model. And now we will see some examples of use of this aleatoric and epistemic uncertainty. So let's go back to our multitask learning problem. Remember, we have the loss function that we want to optimize, and this is a function of the loss functions of the different tasks. And these loss functions are telling us how good we are training to solve the different classification problems. And we had our weights, and we wanted this weight to be a function of the uncertainty. The higher the uncertainty, less priority, less weight. The lower the uncertainty, more precision, higher the coefficient should be. So let's try to see how to determine this. And let us consider, for example, here we can do that, so we can factorize the output and assume Gaussian distribution. So we can represent the likelihood of the multitask model as a factorized product of Gaussian distributions of the different tasks. And here we have the parameter that is measuring the noise of the different tasks. So this sigma is a model observation noise parameter. Okay, so we can factorize this. We can represent it as a sum of the loss functions of the different tasks weighted by the noise or the variance of the different tasks, and with some a more parameter that is logarithm of the noise of the different tasks. So we can do this for the single label, and also we show that this could be extrapolated to the multi-label problem and for the binary cross entropy too. So using this information, we can apply it to our problem, our multitask learning. So let us consider here we have different tasks. We have food, we have ingredients, also drinks, categories. For example, here you can see the different cuisines we are using. And here are the results. So we can see here the ground truth for the dish, for the cuisine, for the categories. Here is the result of our model. So if it is green, it means that dish and cuisine and categories were recognized incorrectly. And if we consider single task for each classification problem independently, you can see that, for example, here the dish was mistaken, cuisine was mistaken, only the categories were ascertained. Okay, or here, for example, for sushi, you can see that our model could recognize correctly, and the single task, for example, recognized the cuisine, but mistook the dish and the categories. So this is really difficult problem, but if we use this multitask problem using uncertainty modeling, in this case, one of the tasks is helping to the other. Okay, so here, for example, we can see how it works even on ingredients. Ingredients is very, very difficult because some of the ingredients will be hidden, like salt or pepper, but still our model is able to recognize what ingredients this dish could have. Here, for example, you can see the predicted are the olive oil, the minced garlic and thyme, and also the ground truth is coinciding. In this dish, for example, also our model recognized the dish, but couldn't recognize very well the ingredients. It is very difficult. But for example, for chicken curry, here you can see that it successfully recognized it even. So if you have some curiosity, you can go to our API demo. It is www.logview.es/demo. Here there are 100,000 of images of food. You can choose your one's favorite, and you can see how the group and the dish recognition works. Okay, and here we can see the result, how the accuracy improved. For example, for the single task, it is much worse, except for the ingredients. For reasonable, it is for reasonable causes. But for example, you can see that accuracy was improved for the dish and for the categories. And even when we consider, for example, here multitask accuracy, where we want that on images, we consider what is the percentage of images of food where all categories, all tasks are done correctly. So it is much more skeptical accuracy than measuring separately. So we can see that in this case, our method improved the classical multitask learning and the single task learning. Now, let us think about epistemic uncertainty. So in the epistemic uncertainty, we think about the noise of the model and how to measure the noise of the model, not of the data. So usual way is to use Bayesian neural networks instead of neural networks. And in the Bayesian neural networks, the difference is that in our arcs that are connecting the different neurons, instead of one scalar that is trained in the training process, we have a distribution. And this distribution is giving us the amount of uncertainty we have in our model. So the smaller the uncertainty, this variance will be smaller. The higher the uncertainty, this distribution will have a higher variance. So the problem here is how to estimate the distribution of all these arcs. Now, the problem is that, remember, we in neural networks, we have million parameters. So now instead of estimating million of parameters, we need to estimate millions of distributions. And this is really very, very complicated, difficult task. And in the Bayesian neural networks, what we want to do is we want, instead of taking the single set of weights, what we usually have, that maximize the posterior distribution, we consider all possible weights weighted by their probability. Okay, so in this case, we see that we have here the likelihood, and this is weighted by the distribution of the weight in order to compute the posterior probability, the final probability of our model. So the likelihood is weighted by the posterior probability of the model weights given the data. Now, how to compute the posterior probability of the model weights? And this is really this part. This is really hard. So there are two main approaches. One of them is the variation of inference, where we consider not all kinds of posterior probability functions, but we restrict to a variation of family that is more easy to compute. The point is that in this case, we have a low variance because we are restricting to a variation of family, but we have a very high bias because we restrict to this variation of family. And we lost a lot of distributions like here. An alternative is to use sampling methods like Monte Carlo methods. So in this case, we will have high variance because we can sample all over our space, but we will have very low bias because we don't apply any assumption. So Gar and Gahramani showed that when we use the dropout at inference time, in fact, we are doing an uncertainty estimator of our model. And the way to do this is infer multiple times the label given the data, each time sampling a different set of nodes to drop out, average the prediction of the final to get the final prediction, and calculate the sample variance of these predictions. So this will give us information about or estimation of the model uncertainty. That is, it will give us estimated of the epistemic uncertainty. Okay, and for this, what we do is we use this epistemic uncertainty of our model using K Monte Carlo dropout simulations. Okay, good. So now let us think how we can use it. For example, remember the second example when we have some difficult classes that have much more data. So how can we use a model in order to augment these difficult classes and make our model less less prone to the noise? So usually, in order to help to the difficult classes, we do data augmentation. So we can get the original image, we can change brightness, color, contrast, sharpness, or combination of these, and we can get a lot of images. But the question is, are there some other ways to create more images that are not so trivial transformation like this one? And maybe some of you have thought about creating synthetic images. So in order to create synthetic images, for this we can use GANs. And GANs have been declared how as the most interesting and promising area of research in the last 10 years in machine learning, according to LeCun, that is the vice president and chief AI scientist in Facebook. So what are the GANs? The GANs are a combination of generator and discriminator. So the generator try to generate a new image, and the discriminator try to detect if this image is fake or real. Okay? So we can use these GANs in order to create synthetic images, but not from all classes, but just for these classes that have much more uncertainty. Okay, so what we can do is we can estimate the different classes and their epistemic uncertainty, and then use some GAN in order to create some synthetic images of these classes, and in this case, augment this part of our data set. So when we use this, for example, you can see here, this is the original image. So when we use synthetic GANs, so for example, SynGAN was used here. So we create all these images. As you see, they are transformations of the original image. Or here, for example, from these original images, here it create this one, or from this one. So you see that, for example, here it removed this, the cheese, or here it removed also the cheese, or here, for example, it changed it and rotated and shuffled a little bit the food. But also we can use other GANs like attention GAN. For example, attention GAN allow us to learn to transform from one class to another. So for example, here we train it attention GAN to learn to generate pizza from spaghettis or spaghettis from pizza. So you see, for example, when you generated the spaghettis, it kept very much the shape, but it put this texture that are very much coming or typical for the spaghettis instead of the pizza. Or here, for example, from this pizza, it generated this dish of spaghetti. So you see that all these spaghettis were artificially generated. Okay, so we can do this kind of different data augmentation with taking into account the uncertainty of the classes. So doing this class conditional data augmentation using GANs. And you can see that using this on different models. So for example, the accuracy improved significantly from 61 to 65. Or here, for example, on another data set on Food 101, it improved from 77 to 82, almost with 5%. And but also the epistemic uncertainty also was incremented as we added more synthetic data. And last example of using epistemic uncertainty would be, let us imagine a scenario. Let us imagine that we visit Mexico. So, and in Mexico, we want to recognize the food. So my question is, my classifier that is trying to be as general as possible, but on what is the sense that when we go to Mexico, our classifier should recognize dishes, for example, from Norway. The probability to eat food from Norway is very, very, very low. So what we can do here is to make our classifier hierarchical classifier. So first, it recognizes what kind of food, what kind of cuisine we have, and then just recognize the dishes from this cuisine. So I can recognize the American, Germany, Portuguese, Turkey food, etc. And then once I know which is the cuisine, and I can apply a specific for this cuisine classifier. So instead of having one classifier that is recognizing all over the world that are, according to the Wikipedia, more than 100,000, what we can do is recognize first the cuisine and then recognize the food, but only for typical for this cuisine. Now, this problem, this hierarchical classifier has a problem. And this problem is called as the error propagation problem. It means that if I mistake the cuisine, I say, okay, this was Mexican food, but it was Norwegian food, it will never recognize then the Norwegian food because it will only recognize the Mexican food. So it means that when we apply this cuisine classifier, we should apply it only when we are very, very, very sure that our classifier is very good classifying cuisine. It means that I need to measure the uncertainty of this classifier. So what we can do is we can try make a more complicated hierarchical classifier where we put several constraints in order to get to be sure that we can apply this hierarchical classifier. For example, what we can do is we can classify the food and get without any dropout. We try to classify which is the cuisine, like German. Then we drop out, we can also classify and see what is the result. Again, it says German. And then we estimate for the German cuisine what is the epistemic uncertainty. So if we see that the class with less uncertainty is the German food, the German class, then we can apply only the classifier of the German food. But otherwise, we should go for the generic classifier. So let's see how it works. We can see that if we use this different, if we don't use any constraint, but just apply the hierarchical classifier, so we can see that our classifier has less accuracy than if I use the flat classifier with all classes of all cuisines. But if I use this hierarchical classifier using all these three constraints, that is to coincide the classifier for the food and less uncertainty, no, using and without using the dropout to estimate the dish, then we have better results than if we use the flat and the hierarchical classifier. And here we can see that it is very important to have these three restrictions because we only have some of the restrictions, we don't have good enough accuracy, but we really need to be very sure that this is the right classifier for the cuisine in order to go for the hierarchical classifier and then apply only the specific dishes. Okay, so last conclusions, I would say that food image work brings us huge amount of data and computer vision questions. And transfer learning and its problems like multitask learning open new opportunities to make research in this line. And uncertainty modeling is a hot topic with many open questions and challenges. And here we can see that a critical relation between elements helps to the classification. So we saw two examples of uncertainty, aleatoric uncertainty, where we use the uncertainty estimated from the data in order to weight different tasks and make our multitask learning model more precise. And we saw how epistemic uncertainty can be used in two situations, like for example, to make more robust hierarchical classifiers and get a good view to improve condition scalability, but also create class conditional data augmentation and get much more robust and precise results. And a huge impact of food analysis is expected from point of view of science. We see that we can make a lot of different research questions. What is the right transfer learning? What is the right way to apply uncertainty? What kind of uncertainty can be helpful for aleatoric, epistemic, how to apply? But also, speaking about food, we can think about a lot of real-world applications, especially important for the society, as problems as diabetes, obesity, cardiovascular problems, or other problems where diet is really highly related to the healthy habits and healthy lifestyle of the people. Thank you very much. If you have any questions.
Thank you, ma'am. Thank you very much. Thank you very much for. But we could have gone through a better time span because yeah, it's not possible yet from our side. And thank you very much for sparing answering such kind of questions from your side. I'm very delighted to have you over here. And now I would like to request our participants to put to ask some questions or put some questions on the chat box. If you have any questions for our you can ask. Or Dr. Paul, hey, Mr. Paul, Mr.
Hello.
Paul, if possible, you can unmute the. Hello.
Hello, Professor Radeva, can you hear me? I'm Samarjit.
Okay.
Hello.
Hello.
Okay.
Hello.
So I have one question. So actually, for considering those types of uncertainties like aleatory uncertainty and epistemic uncertainty, so can I use some fuzzy technique other than probabilistic technique for that type of model?
You mean, can we use some probabilistic techniques in order to estimate the uncertainty?
Yes. Any fuzzy technique? Fuzzy technique? Fuzzy uncertainty? Fuzzy based uncertainty?
Yeah. How do we estimate the uncertainty, you mean?
Yes.
Yeah, well, there are different ways to estimate the uncertainty. Remember, for the aleatoric uncertainty, for example, we estimate through the Gaussian distribution of the different tasks. So
I know, yeah.
When you measure the variance is related to the uncertainty of the aleatoric uncertainty of the data. And in the epistemic uncertainty, for example, one possibility is to use dropout in the inference procedure. So in this case, you are estimating the epistemic uncertainty, or you can apply Bayesian neural networks, where
Bayesian
you
neural network.
directly have in the estimation of the different distributions. Also, you have the variance that is giving you information about uncertainty of the model.
Okay, thank you. One more question. So actually, if there are some class imbalancing factor in the data set, so how we considered such type of thing?
How we consider what? I hear you very well.
Yes. Some class imbalancing factor in the data set.
If there is class imbalance, okay, so this is additionally making more difficult the problem, and this is related to what we discussed. For example, the second example, when different classes can have different errors. So, for example, in this case, we can use class conditional data augmentation, as I mentioned. Yeah, so you can estimate the uncertainty of the classes and then try to augment or improve on these classes. So if your data are imbalanced, it is very highly that also in these imbalanced classes, we will have much more uncertainty.
Thank you very much.
Welcome.
There is one more question from one of the participants. That which technique is best for object classification?
Well, it depends very much. That is, you know, that there is this challenge for on ImageNet that is showing which are the best models. Today there are a lot of very well behaving for object classification. So you can go for EfficientNet, you can go for Inception ResNet V2, a lot of good models, and then you always try a few of them because there is not only one. Maybe it depends very much you want to classify. We cannot say that as like but we get the 4 or 5 best models and apply and see which is the best for us. So for us, Inception ResNet V2, for example, works quite well. ResNet is a good, more simple model, so you should try. Maybe last question, if there is any last question, because I really need to leave. I'm sorry for this. Can likelihood probabilistic model be used for clustering purposes? Definitely, for sure. Yeah,
Eshan sir, is there any question?
Yes, ma'am, I'm sorry. One more question. Can childhood probabilistic model be used for clustering purpose?
Yeah, definitely.
No, sorry, I'm sorry. Sorry. Can likelihood probabilistic model be used for clustering purpose?
Definitely, there it can be used, and also now there is also very recent and nice works on unsupervised learning, deep learning. So I suggest to have a look on this for clustering purposes. And shall you use faster RCNN? Definitely, this is a good model, but this is much more for object detection. So thank you very much. Thank you very much, everybody, for the nice questions and for your attention. If
Thank
you
you.
have any other,
Thank you. Thank
also
you.
you can.
Thank you so much.
You
Ma'am,
can
can we share the recordings? Is it permissible? We
yes,
can do it. Well, thank you.
sure.
Thank you very much. Thank you very much. Thank you for
Thank
coming,
you.
ma'am. I'm putting the vote of thanks. Thank you, ma'am, for being with us. We are very delighted and we are very pleased to have you with us. And we are very sorry for making it for 1 more hour. It's not good from our side. And actually, you told that as per your time zone, it can wait up to 12. So I'm sorry for that. So thank you very much to our respected invited speaker, Dr. Petia, for delivering such a wonderful talk on deep learning on the food imaging. And I'd like to thank our honorable chairman, sir, our chief patron, our principal, sir, register, sir, and vice chairman, secretary of the institutes, and all my team members for this successful ending of this day 1 of this concerned webinar of EIM in 2020. Thank you, ma'am. I will come back to you soon after this completion of this session. Thank you very much. Stay safe, stay healthy.
Thank you. Safe. Take care. Bye bye.
Bye bye, ma'am.